Welcome to the elementary synthetic geometry-based introduction to inversion of the real plane with respect to a circle course, episode 3, lecture 3, in which we will prove our first 5 theorems and solve our first 5 problems. The topology of this lecture is shown on the left-hand side of your screen over here, which means that we will present the material in this episode in the following order. First, we will prove the theorem number 1, followed by the proof of the theorem number 2, followed by the proof of the theorem number 3, followed by the proof of the theorem number 4. Then we will take a short break and solve our first 2 problems, problem 1 and problem 2. Then we will move on to the proof of the theorem number 5, and we will conclude this episode with the solution of the problems 3, 4, and 5. In general, it is okay to consume this material in any which order you like or you want, but for best results, I constructed this material and will present this material in this specific order because, for example, the problem number 5, and the last problem in this episode, is birthed by the fact that the solutions of the problems 2 and 4 can be compared to the solutions of the problems number 1 and number 3 in a certain way, and thus the question that we will ask in the problem number 5 is born. So as you can see, this material is spliced together in such a way that it favors the consumption of that material in this specific order or over the timeline shown with this arrow. And the last remark that I'm about to say applies in equal measure to both theorems and problems. I suggest that you practice mathematics correctly, as I explained in season 1 episode 2 on the Problema channel. And the moment you hear the formulation of any theorem in this course, or the moment you understand the statement of any problem in this course, we recommend that you put this video on pause, walk away, and try to either generate a proof of the corresponding theorem on your own, or try to solve the corresponding problem on your own as well. The theorem number 1, shown over here, states that under the inversion of a plane with respect to a circle C that has the point O as its center and R as its radius, with positive power captured over here with plus R squared, so this is important, with positive power, any point, such as the point A, located precisely on the circle of inversion C, is taken back into itself. For a proof of this theorem, we observe that regardless of where the pre-image point, such as the point A, is located in the parent plane, according to definition 1, recall our definition 1, condition 3, we have it that the distances of the image point A from the center of inversion and of the image point A prime from the center of inversion are locked into the following relationship. Their product is equal to R squared, where R is the radius of the circle of inversion. But in our case, we're told that the pre-image point A is located precisely on the circle of inversion C, and recalling our discussion at the end of the previous lecture, we remember that that means that the distance from the point O to the pre-image point A is precisely r. The distance from the center of inversion, O, to the pre-image point A is precisely r, where r is the radius of the circle of inversion. And that means that the following workhorse relationship between the distances from the center of inversion to the pre-image and image points can be rendered as follows: r times the distance from the center of inversion to the image point A prime, that is equal to r squared. Since the length of the radius of the circle of inversion, or the radius of inversion, is not 0, we take it that r is not 0, it is permissible to divide both sides of this relation by a single copy of r. Divide, divide, and from here it follows that the distance from the point O, from the center of inversion, to the image point A prime in this case is captured with this relationship over here. And in general, if, for example, temporarily we embed the whole situation into 3 space, what does that relation mean? What does it mean? In the context of 3 space, this relation means that the point A prime can be located anywhere on the sphere that has the center of inversion O as its center and R as its radius. However, the transformation that we're studying in this course is strictly planar. It means that all the material of interest is located in the ambient and the parent plane. Consequently, this relation means that the image point A prime under the inversion of the given plane with respect to a circle C centered at the point O and the radius R with positive power must be located where? Must be located somewhere on the circle of inversion C precisely. This is what this relation means. However, now we go back to our definition 1. Definition 1. And recall condition number 1. According to this condition, the pre-image point, the image point, and the center of inversion must be what? They must be collinear. That was one of the requirements that we stipulated. The point O, the center of inversion, the pre-image point A, and the image point A prime all belong to one and the same straight line. I use the fancy name lambda just to imprint it onto our collective mind that the 3 points of interest are collinear. And now, lastly, we go back to our definition 2. Definition 2, we defined the inversion of the plane with respect to a circle with positive power. And according to that definition, if the inversion of the plane with respect to a circle is with positive power, then the pre-image point A and the image point A prime are located on the same side. Recall our definition that in this case, the center of inversion, in our case the point O, the pre-image point A, and the image point A prime are located on the same side with respect to the center of inversion O. Combining these 3 facts, 1, 2, and 3 together into one, there is only one conclusion. Under the inversion of a plane with respect to a circle with positive power, any point on the circle of inversion is taken back into itself, which means that in this case, the point A prime is exactly the same as the original point A. And this conclusion completes our proof. If you have any questions, use the comment section to this video. Ask your questions away. And here, before we'll move on to the next theorem, we will note that in general in mathematics and in geometry in particular, if a given point as a result of a particular geometric transformation does not move anywhere and remains stationary, such as the point A in this case, when the power of inversion is positive, such a point is called stationary. In this case, let me write it down over here, is called stationary, is called fixed. The official name for the stationary point is fixed. The point is fixed, or maybe in some texts you will see the name stationary. Now that we're done with the study of what happens to a sample point that belongs to the circle of inversion when the power of inversion is positive, we will move on to the theorem number 2, which will study what happens to the point on the circle of inversion when the power of inversion is negative. According to the theorem number 2, under the inversion of a plane with respect to a circle C that has the point O as its center and R as its radius with negative power, as shown over here with the minus sign in front of the square of the radius of inversion, any point on the circle of inversion, such as the point A, is taken into a point that is located on the circle of inversion C diametrically opposite to the original point. In other words, the point A, for example, is taken into the point A prime such that the distance between the pre-image point and the image point is precisely the diameter of the circle of inversion, or the distance that is equal to twice the length of the radius of inversion R. And again, pay attention to the fact that in this case, the power of inversion is negative, and it is instructive to pull up your proof that you generated for the theorem number 1 and analyze exactly which parts of that proof must be changed in order to generate a correct proof of the theorem number 2. Here we will reason in the following way. Also, we will begin with the workhorse relation that will serve us well throughout this course, this relation shown over here, and state that regardless of where the pre-image point, such as the point A, is located in the parent plane under the inversion of that plane with respect to a circle C that has O as its center and R as its radius, regardless of the power of inversion, the distance of the pre-image point from the center of inversion and the distance of the image of the pre-image point to the center of inversion are locked into the following relationship. Their product is equal to the square of the radius of inversion. But again, as in the previous theorem, still we have our pre-image point located on the circle of inversion, and that means that the distance between the center of inversion and the pre-image point A is what is precisely R. So this step is exactly the same. The first step is exactly the same. Definition 1, condition 3. The fact that the distance between the center of inversion and the pre-image point is R is exactly the same. The conclusion here is exactly the same. The assumption that the length of the radius of inversion is not zero, exactly the same. The cancellation of one copy of the radius of inversion on either side of this relationship is also the same. the fact that the distance between the center of inversion and the image point A prime is equal to r is the same. The general observation that in the context of the 3 space, in other words, if we embed all the interesting material into 3 space, in general, this relationship means that the image point A can be located anywhere on the sphere that has its center at the center of inversion and r as the radius of inversion. That is also the same. The fact that we will mention definition 1, condition 1, that all 3 points of interest, the center of inversion, the pre-image point, and the image point are all collinear, still exactly the same. So what does change for the proof of the theorem number 2 with respect to the proof that we generated for the theorem number 1? What changes is the definition that we use for the power of inversion. Instead of taking the definition for the positive power of inversion, we'll go back to definition 3, and we use the fact that the power of inversion in this case is what? Negative. And according to that definition, what is the mutual juxtaposition of the points of interest in this case? Well, remember that the power of inversion is negative if and only if the center of inversion, let us even use the red chalk, the center of inversion, O, is located in between the image point and the pre-image point. Let's say this is the point A, this is its image A prime, and combining these 3 facts, that the distance from the center of inversion to the image point A must be precisely r, all the material, all the objects of interest are coplanar with the center of inversion and the circle of inversion. The points, the center of inversion, the pre-image and the image are still collinear, but in this case, the center of inversion must be in between the pre-image and image point. With the third fact, combining the fact number 1, number 2, and number 3, what conclusion do we draw? That is precisely the conclusion that we draw, that in this case, that is in the case when the power of inversion is negative, our sample point that is located precisely on the circle of inversion is taken into its image point A prime such that the distance from the center of inversion to the pre-image point is exactly the same as the distance from the center of inversion to the image. The distance OA is equal to the distance OA prime, but that is not enough. Combining this fact with this, definition 1, condition 1, precisely plus this means that the point A prime is such that the distance between the pre-image point and the image point is precisely the diameter of the circle of inversion, or twice the length of the radius of inversion, and that can happen only when the point A prime, the image of the original point, is diametrically opposite from the image point A. In other words, in this case, the center of inversion is contained by the straight line A prime, and that completes our proof. And now that we understand how the inversion of the plane with respect to a circle acts on the points that are located precisely on the circle of inversion under both positive and negative powers, we will look at the theorem number 3, which is an easy consequence of the theorem number 1 and the theorem number 2. According to the theorem number 3, under the inversion of a plane with respect to a circle C, that has the point O as its center and R as its radius, the circle of inversion is taken back into itself, regardless of the power of inversion, positive or negative, and the proof of that theorem follows directly from the proof of the Theorem 1 and the Theorem 2. Indeed, recall that in Theorem 1 we proved that under the inversion of a plane with respect to a circle C that has the point O as its center and R as its radius, any point shown over here in red that is located precisely on the circle of inversion is taken back into itself, and thus we now know that this point is called fixed. This point is fixed when the power of inversion is positive. In this case, each and every point that makes up the circle of inversion remains fixed, and that precisely means that the circle of inversion in this case, we use white chalk, the circle of inversion C is taken back into itself when the power of inversion is positive. And in the theorem number 2, we prove that under the inversion of a plane with respect to a circle C that has O as its center and R as its radius, any point such as the point A that is located precisely on the circle of inversion, when the power is negative, that point is taken into its diametrically opposite image on the circle of inversion still. But what does that mean? Well, in our proof of the theorem number 2, we can, with the same success, exchange the roles of the points A prime and A. In other words, we can construct the same proof using the symbol A prime for our pre-image point, and then its image point will be A. And what does that mean? Well, that means that under the inversion of the plane with respect to a circle, the points on the circle of inversion that are diametrically opposite with respect to each other under the inversion with negative power do what? They trade places. And that means that under the inversion of the plane with respect to a circle with negative power, the circle of inversion gets reshuffled or gets rewired or rebuilt point-wise in a non-trivial fashion. In other words, every point that makes up the circle of inversion under negative power is moved to its diametrically opposite image. But after that rewiring, the circle of inversion still remains one and the same. It is located where it was located prior to the inversion with negative power. Its radius is exactly the same, as is evident by the fact that the distances between the pre-image and image points is 2r everywhere. And that means that the statement of our theorem is correct even when the power of inversion is negative, depicted over here with the minus sign in front of the square of the radius of inversion. And that completes the proof of the theorem number 3. Again, if you have any questions, use the comment section below. And before we move on to the theorem number 4, we will observe that when a given point and under a transformation remains stationary, doesn't move at all, or called fixed, then the entire shape or the entire figure is called invariant. This is the word that applies to the collection of points that make up this particular figure. That figure is called invariant, and the transformation that produced that invariant figure is called the identity transformation. And these identity transformations actually come in a variety of flavors. It pays to understand this terminology because you will see it again and again in, for example, the theory of groups, where, for example, let's say we take a square, and then instead of inverting this square with respect to a circle or doing anything like that, we simply take and reflect, and we reflect that square with respect any one of its, how many? 4 axes of symmetry. Then what will happen under such a reflection? Under such a reflection, every point that belongs to the square except for the points where the axis of symmetry, the chosen axis of symmetry, intersects the corresponding sides of the square, will what trade places in a similar way as the points that make up the circle of inversion under negative power trade places. For example, if we reflect this square with respect to this axis called, for example, L1, then this point will jump over here, this point will jump over here. These 2 points will be what? We already know the terminology. These 2 points will be fixed, but all the other points of the square will be rewired or shaken in a non-trivial fashion. They will trade places again, but as a result, the square will be taken still back into itself. According to the Theorem 4, under the inversion of a plane with respect to a circle C that has the point O as its center and R as its radius, with any power, positive or negative, any point that is located strictly inside of the circle of inversion C and that is distinct from the center of inversion is taken into a point that is located in the parent plane strictly outside of the circle of inversion. And for a proof, as usual, we go back to our trusty relation that locks in the distances from the pre-image point to the center of inversion and from the image point to the center of inversion, stated over here. The product of these distances is equal to the square of the radius of inversion r. Algebraically, the verbal requirement that the point A is located strictly inside of the circle of inversion and is distinct from the center of inversion means what? It means that the distance from the center of inversion to the pre-image point A is strictly less than r. This is our algebraic rendition of the fact that the sample pre-image point A is located strictly inside of the circle of inversion C. And from that, it follows that since all the magnitudes in question are strictly positive, the reciprocal of this relationship translates into follows: 1 over the distance from the center of inversion to the pre-image point A must be strictly greater than R. Now we take our workhorse inversive geometry relation and we write down the expression for the distance from the center of inversion, O, to the image point A prime. That means that that distance must be the square of the radius of inversion divided by the distance from the center of inversion to the pre-image point A. Now we bring in this relation over here, and that means what? That means that since the distance from the center of inversion to the pre-image point is strictly less than the radius of inversion, its reciprocal image is strictly greater than the radius of inversion. That means that the whole thing here is strictly larger than r squared over r. Again, we operate under assumption that, of course, the most interesting case is when the length of the radius of inversion is not 0. This manipulation is legal. Canceling one copy of r in the numerator and the denominator, we have it that this cancellation produces a single copy of the length of the radius of inversion, and that means that the distance from the center of inversion to the image point A prime is strictly larger than R. And again, this algebraic relationship translates back into the language of geometry in such a way that we state that the point A prime, the image point A prime, is located in the parent plane in such a way that it is strictly outside of the circle of inversion, precisely because we have a strict inequality. That distance is greater than R. And again, remember that this theorem, the theorem 4, applies to inversions with both powers, positive and negative. We now know that the difference between the type of the power of inversion only affects the mutual juxtaposition of the image points A and A prime, but it does not affect the algebraic essence of the relationship that ties the distances from these points to the center of inversion. And that concludes the proof of this theorem, which states that under the inversion of a plane with respect to a circle C that has the point O as its center and R as its radius, any point A that is located strictly inside of the circle of inversion and is distinct from the center of inversion is taken into the parent plane into a position that is located strictly outside of the center of inversion, again, regardless of the type of the power of inversion, positive or negative. Now we will take a short break from generating proofs for our theorems and solve our first two problems. In the first problem of this course, using the Euclidean tools alone, a straight edge and a compass, we're asked to find the inverse image of a given point under the inversion of a plane with respect to a circle with positive power when the pre-image point is located strictly inside of the circle of inversion and is distinct from that center of inversion O, that is. When we're told that we're given the circle of inversion, unless it is otherwise noticed, we will take it that the location of the center of inversion, the point O in this case, is given, and the length of the radius of inversion is also given. We're also given a sample point that is located strictly inside of the circle of inversion C, and that is distinct from the center of inversion O in this case. Under the inversion that is carried out with positive power, we're asked to construct the inverse image A prime using the Euclidean tools alone, a compass and a straight edge. So we're asked to come up with an algorithm following which ambiguous without any ambiguity, with absolute certainty and correctly, we locate that inverse image of the point A, in this case when the power of inversion is positive. Again, we recommend, as I explained in season 1 episode 2, put this video on pause, walk away, try to solve this problem on your own. It is okay to fail initially if you gave it an earnest and honest effort. You created a paper trail which shows I tried this, I tried that, I tried this, I tried that, I stuck over here, or I only partially got through the problem. And when you came back and you watch our presentation, only through your personal effort, even if you failed, it is okay, will you gain the academic benefit by the time that you spent on thinking about this problem and inhaling all the material that we covered so far. Most, if not all, students who take on this course, they come up with the following construction that is quite popular. As the first step, as the step number 1, which we will carefully mark, we construct a straight line that passes through the center of inversion and the given pre-image point. We will name that straight line L. L by definition will be our straight line that passes through the center of inversion and the given pre-image point. That task can be carried out with the Euclidean straight edge. In some sense, as a theoretical tool, this is what this tool was born for, and we will carefully mark it as our step number 1. Why are we doing it will become evident when we will take on the problem number 5. That is the first step. In the second step, we construct a perpendicular, which we will call P, through the point L, through the point A, and perpendicular to the straight line L that we constructed prior in the first step. That construction can be done with Euclidean tools alone. Many students know a 4-step construction for that problem, but out of band, after the second problem, I will tell you how to carry out that construction in 3 steps, not in 4, but in 3. In other words, the straight line P is perpendicular to the straight line L constructed in the previous step at the pre-image point A, so the angle at A is right. That technically, that perpendicular P will intersect the straight line, will intersect the circle of inversion at 2 distinct points. We will call one point B, the other one is X. It doesn't really matter which one is which you pick, doesn't really matter. We pick one. Let's say we pick this one. This will be our point B. And as the step number 3, so this will be the step number 2, we carefully mark it down. As a step number 3, we connect the points A and B, or we draw a straight line through the points O and B. I will just call it the straight line OB. I will try to minimize the number of symbols that we have to use, and we are almost done. On the step number 4, this will be our step number 3. This will be step number 3. We construct a straight line. I will call that straight line tau, that will be perpendicular to the straight line OB at the point B, shown over here. Let's see if I can do it by eye, by hand. Perpendicular to OB. We will call that straight line tau, and that straight line tau will intersect our straight line L that we constructed in the first step precisely at a single point that will be the sought after inverse image of the point A, located strictly inside of the circle of inversion under positive power. That point will be located right here. This will be our point. Where should I write it? A prime, right here. Our point A prime. And if you manage to come up with this construction then on your own, then that is very good. That is very good. Let's carefully write down that this straight line is straight line number 4. So we have 1, 2, 3, 4. Remember the sequence or the order, because now when we will take on the problem number 5, we will discover that there is something going on with this order of straight lines that we construct when we deal with positive power of inversion. But constructing the inverse image using the Euclidean tools alone in this manner, that is, by the way, absolutely correct, is one thing, but generating a proof that this construction is indeed an algorithm that recovers unambiguously and correctly the location of the inverse image of the point A prime is also your responsibility. So essentially, and we will see it in the number of upcoming problems, all these proofs, they follow more or less the same template. The template revolves around Euclid's Elements, book 6 proposition 8. Essentially, that is what it is, the link to that theorem that was put together and made available on the internet for the rest of us by Dr. Joyce is in the comments section. So what do we do here? Well, essentially we have by construction the parent triangle OBA prime. This triangle is right with the magnitude of its interior angle at B being right. From that right angle vertex, as Euclid says, emanates a straight line that falls directly onto the base, which in this case the hypotenuse of this triangle, and the angle under which the straight line BA falls onto the straight line LOA is right. This angle is right. Consequently, this height of this triangle OBA prime partitions this triangle into smaller right triangles OAB and ABA prime. Each of these triangles is also right. These two smaller triangles similar to each other, and each one of these triangles is similar with the parent triangle. How can we see that? Well, let's take the smaller triangle OAB and the larger parent triangle OBA prime. In this case, these two triangles share one and the same angle. Let's call this angle over here as alpha. This is the angle alpha. Alpha is one and the same by magnitude. The right angle at the vertex A and at the vertex B of these two right triangles are equal by Euclid's Elements, Book 1, Proposition 32. The magnitudes of all the interior angles of any non-degenerate plane Euclidean triangle sum to pi radians. Thus, if we have two angles equal to two angles in two triangles, the magnitude of the remaining angle must match by that proposition. That means that the magnitude of this angle right here, this one, we'll call this angle beta, in the smaller triangle OAB must match the magnitude of which angle? Must match the magnitude over here of this angle. This will be beta. Likewise, now we shift gears and now we concentrate on the smaller right triangle BAA prime and the parent triangle OBA prime. These two triangles share one and the same angle at the vertex A prime. They have right angles at the corresponding vertices A and B, and that means by the same Euclid's Elements, Book 1, Proposition 32, the magnitude of the remaining angle must be the same for these two triangles, which are what? Well, in this case, the remaining angle for the smaller triangle B, A, and A prime is this one. I should use the green one. I apologize. The green. This one. This will be alpha. And this must match the angle at the vertex A of the parent triangle. And now we see that by that virtue, our smaller triangles OAB and BAA prime have the same magnitudes of their interior angles, and by AAA, angle, 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 all these three right triangles are similar. And here comes Euclid's Elements, Book 6, Proposition 4, another one, which states what? The lengths of the sides of two triangles that are similar by AAA, about the same angles, are in the same proportion where the corresponding sides lie opposite equal angles. So now we want to prove that, what do we have? The points O, A, and A prime are collinear. That is good. That's condition 1 of definition 1. The points A, the pre-image, and A prime image are on the same side with respect to the center of inversion. Oh, that's good. That's our what? Definition 2. The power of inversion is positive. Now we need to concoct our favorite product, OA. The distance between O and A times the distance between O and A prime must be equal to the square of this radius. How do we do it? Well, we just pick the advantageous right triangles. And what are these triangles? Well, the smaller triangle, in this case OAB. In this triangle, let's pick our distance already OA. Let's lock it in. In this triangle, the side OA lies opposite to the angle beta shown in red. In the parent triangle OBA prime, which side lies opposite to the red angle beta? Well, that's the side OB. So boom, we have our OB. Now, in the smaller triangle OAB, we also relate this side to the side OB that lies in the smaller triangle opposite what? Right angle at A. Which side of the parent triangle OBA prime lies opposite its right angle at B? Well, the side OA prime, the hypotenuse. OA prime. There you go. Cross multiplying, we obtain that the product of the distance from A to O times the distance from O to A prime is equal to OB squared, which is precisely the distance between the points O and B is precisely R, the length of the radius of inversion. This completes the proof, and this completes the solution of the problem 1. Again, my suggestion to you is to carefully write down the sequence of steps which we used in order to produce the inverse image of the point A that is located inside of the circle of inversion when the power is positive. 1, 2, 3, 4 as a tangent, step number 4. 4 tangent. Take a good note of this, and for my books and for my experimentation purposes, I use the free software called GeoGebra. You can use, of course, any of your favorite graphing software packages to do all these experimentations, but it wouldn't be the last thing in the world if you grab the physical piece of paper, physical compass, and a physical straight edge and try to come up with all these constructions in the physical world. Now that we understand how to construct the image of a point that is located strictly inside of the circle of inversion when the power is positive, in the second problem, problem number 2, we will carry out the same task when the power of inversion is negative. In the problem number 2 of this course, we're asked to do essentially the same thing that we were asked to do in the problem number 1, with the exception that this time in the problem number 2, the power of inversion is negative as depicted with the red minus sign in front of the square of the radius of inversion. That is, given the circle of inversion named C that has the point O as its center and R as its radius, and when we say that the circle of inversion is given, then unless otherwise noted, the location of the center of inversion and the length of the radius are known and given, and also given a sample pre-image point A that is located strictly inside of the circle of inversion, but the point that is distinct from the center of inversion, locate its image of that point A using nothing but the Euclidean tools alone, a straight edge and a compass, again with absolute certainty and correctly. Here again, just like we did it with the proof of the theorem number 2, it pays to go back to the constructive steps that we generated in the problem number 1 and compare them to the steps that we will generate in this case, or ask ourselves what steps do we change in the solution of the problem number 1 in order to generate the solution of the problem number 2. Here again, we construct a straight line as the step number 1. We construct exactly the same straight line, let me use the same chalk, L, that passes through the center of inversion and the given pre-image point. We construct that straight line. We name it L. We carefully mark that in our constructive sequence in our algorithm. This is the step number 1. In the second step, we also construct a perpendicular to the previously constructed straight line, but this time not through the pre-image point, but through the center of inversion. Center of inversion O. That straight line, let's say we name that straight line P. That straight line P will intersect our circle of inversion at 2 distinct points, just like in the previous case. That will be the step number 2. The straight line P will intersect the circle of inversion at 2 distinct points. We will name these points B and X. Which one we pick, it doesn't really matter. Out of 2 distinct points, it is enough to pick only one. Let us say we pick this one. I'll pick this one, B. And once we have that, what is the third step? Remember, in the previous solution of the problem number 1, we connected the center of inversion with that point, but now we already have that straight line. So what do we do now? Next, we connect the image, the pre-image point A with the point B, like so. This will be our step number 3. We connect the points A and B, and this straight line is shown over here. I do not show the complete line, but only the relevant part of it that we will need. The interior angles here at O will be right. And the fourth and the final step will be what? Remember, in the previous problem we constructed a straight line that turned out to be tangent to the circle of inversion at the point B, but that straight line was what? It was perpendicular to the straight line that we constructed in the previous step. So here we do exactly the same thing. Let us call that straight line tau, and let's see if I can do it by eye by hand. That straight line is supposed to be, we'll name it tau. It will be perpendicular, straight line tau, that will be perpendicular to the straight line 8B at the point B, and that straight line tau will intersect the straight line L at the sought after point A prime. That will be precisely the inverse image of the point A when the power of inversion is negative. And as usual, it is one thing to come up with the constructive algorithm, and it is another thing entirely to prove that the proposed algorithm is actually correct, and it does locate the sought after object with absolute certainty, and it does it correctly. But again, here we go back to remember what I said in the previous segment. All these proofs follow basically one and the same template that is based on Euclid's Elements, Book 6, Proposition 8, where we have a right triangle A, B, A prime, with the magnitude of the interior angle at the vertex B being right. And from that right angle vertex, we construct a height that falls onto the base, as Euclid says, or the hypotenuse of this triangle, A prime in this case. And that height partitions the parent triangle A, B, A prime into 2 smaller triangles, B, OA prime and BOA, each of which is right, and all three triangles in this case are similar by angle, angle, angle. I already proved that in the previous segment. I will not be doing it again. I will just notice that if we designate the interior angle over here at A as alpha, and the interior angle over here, the smaller one, as beta, then we will have these angles partitioned thus. This will be beta, and this angle right here will be alpha. And all we have to do is again fish out from this jumble of right triangles the advantageous ones, or the ones that tie our distances together. Remember, again, in the previous problem we picked a smaller triangle and a larger one and the parent one. Here apparently we need to work with the two smaller ones. Why is that? Well, here it's book 6 proposition 4. Book 6 proposition 4. The lengths of the sides about equal angles in, as Euclid puts it, equiangular triangles are in the same ratio or in the same proportion when the corresponding sides lie opposite equal angles. And in this case, we consider the triangle BOA and BOA prime. These triangles are similar by AAA, angle, 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 and we splice the needed distances into the works over here. Which way? The distance from the center of inversion to the pre-image point in the triangle BOA, this distance lies against the angle that we marked as beta. And in the smaller similar triangle BOA prime, which is right, which side in that triangle lies against the angle with the same magnitude beta? Well, it's the side OB, so this will be the distance from the center of inversion to B. Here we relate that distance to the side of the smaller triangle OAB that lies opposite the angle alpha. So this will be the distance from the center of inversion to the point B. And in the smaller right triangle BOA prime, which side of the triangle lies opposite the angle that has the same magnitude as we refer to as alpha? OA prime. This is the side exactly. So that's the distance from the center of inversion to the image point A. From here, cross multiplying, we have it that the distance from the center of inversion to the pre-image point times the distance from the center of inversion to the image point is equal to the square of the distance between the center of inversion and the point B, which is precisely the radius of inversion, and voila, we have it. This is our condition 3 of definition 1. The points O, the center of inversion, the pre-image point A and the image point A prime are collinear. This is the condition number 1 of definition 1. And we also see that the point O is located in between the points A, the pre-image, and its image point A prime in the sense of the axioms of geometry due to the German mathematician David Hilbert. So all three conditions or all three constraints are satisfied, and that means precisely that the point A prime that is constructed with Euclidean tools alone, with the straight edge and the compass, following these 4 steps, is precisely the image of the point A that is located strictly inside of the circle of inversion, that is distinct from the center of inversion, under the inversion of the parent plane with respect to that circle, when the power of inversion is negative. And again, in my book and elsewhere for my experimentation purposes, I use the free software called GeoGebra. You, of course, can use any which free or otherwise graphing software you like, but it wouldn't be the last thing in the world to actually grab a physical piece of paper, a physical straight edge, and a physical compass, and go through the constructions that we outlined in the previous problem and in this one on your own in the physical world. According to the Theorem 5, under the inversion of a plane with respect to a circle named C that has the point O as its center and R as its radius, any point in the parent plane that is located strictly outside of the circle of inversion and that is distinct from the point at infinity is taken into its image point A prime that is located strictly inside of the circle of inversion and that is distinct from the center of inversion for both types of powers of inversion, positive as shown over here and negative as shown over here. The proof of this theorem is again quite straightforward. We begin this proof with our workhorse formula because we remember that according to definition 1 condition 3, regardless of where the pre-image point A is located in the parent plane with respect to the circle of inversion, the distance from the center of inversion to the pre-image point and the distance from the center of inversion to its image point A are locked into the following relationship. Their product is equal to the square of the radius of inversion. But in this case, the geometrically verbal description that the given pre-image point is located outside of the circle of inversion is translated into the corresponding algebra as follows. The distance from the center of inversion to the pre-image point is strictly larger than the radius r, the length of the radius of inversion r. And that means that all the numbers that we are dealing with in this situation are strictly positive. It means that the reciprocal of that relation will say what? That the distance 1 divided by the distance between the center of inversion O and the pre-image point A is strictly less than the length of the radius of inversion R. If we put this relation back into here and express the distance from the center of inversion to the image point A, we will have what from this relation? R squared divided by the distance from the center of inversion to the pre-image point A, and that distance will be less than R squared divided by R, again canceling out one copy of the radius of inversion in the numerator, and in the denominator we arrive at the single copy of the radius of inversion, and then we obtain that the distance from the center of inversion to the image point A prime must be strictly less than R, and that algebraic relation is translated back into the language of geometry as follows. The image point A prime is located strictly inside of the circle of inversion, and because our original pre-image point was distinct from the point at infinity, it follows that our image point must be distinct from the center of inversion, because remember, we agreed, it's a part of our definition, that by the strict letter of the law, so to speak, the point O does not have a genuine image under the inversion of the plane with respect to the circle, but we agreed that the image of that point will be the point at infinity, and conversely, the image of the point at infinity is the center of inversion under the inversion of the plane with respect to a circle. Now, here again, remember that we will say that the proof of this theorem is complete, but we observe again carefully that The theorem number 5 applies to both powers of inversion, positive and negative, in equal measure, because the algebraic representation of inversion is always one and the same, and the only thing that differentiates the power of inversion, the negative from the positive, is the mutual juxtaposition of the image points with respect to the center of inversion. When the power of inversion is positive, then the pre-image and the image points are located on the same side of the center of inversion. And when the power of inversion is negative, then the center of inversion, O, is located in between the pre-image and the image points, in the sense of the axioms of geometry due to the German mathematician David Hilbert. And also, some of our viewers who are paying attention, they probably already realized that the constructive relationship between the images with positive and negative powers are actually quite related. That is, we see that if we are given a pre-image point, then in order to obtain the image of that point with negative power, all we have to do is basically reflect this point in the given circle with positive power, and then rotate this image about the center of inversion by pi radians, and conversely. And in this way, we will obtain the image of the given point with negative power. Conversely means that if we're given a pre-image point and we are seeking the image of that point under the inversion of the plane with positive power, we can reflect this point in the circle with negative power. We will put it on the other side of the center of inversion. But then we can rotate this negative power image of the point about the center of inversion by pi radians, and obtain the image of the given point under the positive power when the inversion is carried out with positive power. So this way we can understand, we will prove that statement more rigorously, more formally in the upcoming lectures, but right now we already see that the constructive essence of the image of the given point with positive and negative powers means that these powers are equivalent, in the sense that if the image of a given point is known under one power, the image of the same point under the remaining power is known algorithmically and right away, basically through the rotation of the plane about the center of inversion by pi radians. In the problem 3 of our course, we are given a circle of inversion, let's say C, that has its center at the point O. The location of that point is given to us. We also know the radius, the length of the radius of that circle of inversion. Let's say it's R, and the name of that circle will be C. We're given a point, as in the previous theorem, A, that is located strictly outside of the circle of inversion, and that is the point that is distinct from the point at infinity. The power of inversion right now will be positive, and we're looking for a Euclidean tools alone, a straight edge and a compass algorithm that will recover the location of the image of that point with respect to the circle C, of course, when the power is positive. Here let's say we have a point right here, given point right here, that's the point A. We go back to our problem number 1, where we carried out the similar task, but that in the problem number 1, the sample pre-image point was located where? Strictly inside of the circle of inversion. But now the point is located, the pre-image point to reflect in the circle C with positive power is located outside of the circle of inversion, distinct from the point at infinity. What is an algorithm for that? Well, again, most, if not all, students come up again with this algorithm that is quite straightforward, and it is basically, in some sense, the steps that we took in the problem number 1, but in reverse order. So, for example, first, we still construct our favorite straight line L, which connects the center of inversion and the pre-image point. That step is standard. Let us carry it out. We draw the straight line through the center of inversion and the given pre-image point. Wonderful. Next, what do? We name that straight line L, and we remember to carefully mark it. That will be our step number 1. We will need that in the upcoming problem number 5. That is actually quite interesting. Next, what we do is we reverse the steps of the solution of the problem number 1. And here right away, we construct a tangent through the point that is located outside of the circle to a circle. We know that there exists 2 distinct tangents to such a circle. Out of these 2 distinct tangents, we need only one, which one does not really matter. And as a side effect, a on the tangent remark, pun intended, it is really amazing in how many different ways such a tangent to a circle through an external point can be constructed. Many different ways. Time permitting, I will put together an episode dedicated just to that one task alone, constructing a tangent to a circle through an external point. It is amazing how much deep, meaningful, and hefty mathematics can be attached just to that seemingly childish task as constructing that tangent. So let's say we managed to construct it. That construction again can be carried out precisely with Euclidean tools alone. That's not a problem. That is exactly possible. We will name that straight line again in our fashion. That will be the straight line tau. That would be the straight line number 2. This is the step number 2. Step number 2, we construct a straight line tau that is tangent to the circle of inversion C. Let us say the tangency point is, let's say, the point B again. We go back to our point B. What does that mean? Well, that means that when we connect the center of a given circle with the point of tangency, like so, the angle at the point B will be what? That angle will be right. What do we do next? What is the third step in this case? Well, if you did not solve this problem correctly on your own, you should see what the third and the final step here is. We construct a straight line. We'll name that line as P, perpendicular. To what? To the straight line L constructed in the first step through the point, which one? Through the point B. Through the point B. That straight line P will intersect the straight line L at the point that is precisely the sought after image of the point A under the inversion of the plane with respect to the given circle with positive power. And how do we prove that statement? So let's say this is our perpendicular. We'll name it P. This was our second step. This was our third step. Let's carefully mark it down. This is perpendicular. The angle between the straight line P and L is right. And the point A prime marks the spot. A prime is precisely the image of the point A sought after. And what is the proof of that statement? Well, the proof of that statement is, again, you should be, at this point, you should be telling me what the proof is. Again, we have how many? We have three right triangles. The triangle O, B, A, B, A prime A, and B, A prime O. These three triangles are similar by AAA, angle, angle, angle. And what angles are these? Well, if we mark this angle as alpha, and if we mark this angle, in other words, the angle BOA prime or BOA is alpha, the angle OBA prime is, let's say, beta. That means that in this triangle, in the triangle BA prime A, this angle will be beta, and this angle right here, this angle will be alpha. The whole thing, as I told you guys before, revolves around Euclid's Elements, Book 6, Proposition 8. Euclid's Elements, Book 6, Proposition 8. The three triangles over here that are right are all similar by AAA. We proved that already several times. So all we have to do now is to fish out the advantageous right triangles and cook up the relation that shows that the product between the distances from the center of inversion to the pre-image point and image point is precisely the square of the radius of inversion. How do we do that? Well, here again, the first advantageous triangle will be the one that carries the distance from the center of inversion to the pre-image point. That will be the right triangle OBA. In this triangle, we're gonna right away capitalize on this hypotenuse, the distance between the center of inversion and the pre-image point. Let's write it down. The distance from the center of inversion to the pre-image point in this triangle. The second triangle that we will use will be the right triangle O, A prime, and B. In this triangle, what side will we work with? Well, in our larger or parent triangle OBA, the side OA lies opposite what? The right angle at B. Which side of the smaller triangle OA prime B lies opposite to the right angle at A prime? Well, evidently the side OB. So this will be the side OB in the smaller triangle. Now we relate the side OA prime, OA in the larger parent triangle OBA to what? To the distance from the center of inversion to the point of tangency, B, OB. And if in that triangle the side OB lies opposite the angle beta, then in the smaller triangle OA prime B, which side lies opposite against the angle that has the same magnitude as beta? Well, it's the side OA prime. Again, OA prime. Cross multiplying this ratio tells us that the product of the distances from the center of inversion to the pre-image point and from the center of inversion to the image point is precisely OB squared, which is, in our case, the distance between the center of inversion O and the point of tangency is precisely the radius of inversion. So we have it. Our product is equal to R squared. And because the power of inversion is positive, what do we have? The points O, the center of inversion, the pre-image point, and the image point A prime are collinear. They belong to our one and the same straight line L. the condition 1 of definition 1 are honored, and the points A, the pre-image, and image A prime are located on the same side of the center of inversion O. Since all three conditions are honored, it follows that the steps that we presented over here using nothing but the Euclidean tools, a straight edge and a compass, exactly produce the sought after image of the given point that is located strictly outside of the circle of inversion, is distinct from the point at infinity, and when the inversion of the plane with respect to the given circle C is carried out with positive power. Now that we understand what is going on with this situation when the power of inversion is positive, we will take on the problem number 4, where the power of inversion will be negative. In the problem number 4, when the power of inversion is negative, as shown with the red minus sign in front of the square of the radius of inversion, we also are looking for an algorithm that uses nothing but the Euclidean tools alone, a straight edge and a compass, in order to locate the image of the given pre-image point A that is located strictly outside of the circle of inversion, and the point A is evidently distinct from the point at infinity. Here we will also, by analogy, go back to the solution of the problem number 2, where we carried out a similar task, but that time in the problem number 2 our pre-image point was located inside of the circle of inversion, and we think that we also will reverse the steps that we carried out in the problem number 2. But upon closer inspection, what do we see? Well, first of all, we construct our favorite straight line L through the center of inversion and the given pre-image point. That straight line L is shown over here. L, this is our first step. Step number 2, we construct a straight line named P perpendicular to the straight line L constructed in the previous step through the center of inversion, just like we did it in the problem number 2. Boom, a perpendicular to L through the center of inversion. That perpendicular will intersect the circle of inversion at 2 distinct points, out of which we only need one. Let's say we take the point named B. We put it on top. We carry out the third step. We connect the pre-image point with the point B with a straight line. This is our step number 3. Boom, here it is. The point B is shown over here. That's where the straight line P intersects the circle of inversion at 2 distinct points. We do not need that. I do not want to pollute our construction with more objects than I have to. And what is the final step? The final step, again, we construct our favorite straight line, which I refer to as tau, perpendicular to the straight line that we constructed in the previous step, AB, through the point B. And here, that straight line is shown in yellow, this straight line right here. This straight line will intersect the straight line L that we constructed in the first step over here at the point A prime, that is the sought after image of the given point A under the inversion of the parent plane with respect to the given circle C, when the power of inversion is negative. For a proof, again, at this point you guys should be reciting the proof by heart with your eyes closed. You do not need me for that. Euclid's Elements, Book 6, Proposition 8, right angle. From the right angle there emanates a height on the base or a hypotenuse. 3 triangles are all similar by side, side, side. The equal by magnitude angles are shown in the same color, alpha, alpha, beta, beta. we cook up or pick the triangles that carry the distances that we need. In this case, what will these triangles be? Well, the two smaller right triangles, the triangle BO and A prime. Here is the center of inversion O. I forgot to mark it, but here it is, O. And the right by construction triangle BO and A. Again, we build the construction, build a proportion based on book 6, proposition 4 from Euclid's Elements. The link to the website that was put together by Dr. Joyce is in the comment section. Be my guest. So here we relate which distance? The distance from the center of inversion to the point A, O, A, that lies against which angle? Against the angle alpha. And in the smaller triangle A prime OB, which side lies against the angle alpha? Well, it's the side OB, exactly. So we will relate it to OB, the same proportion. And the side OA in the triangle BOA that lies against angle beta is what? OB. And which side in the smaller triangle BOA prime lies against the angle beta? Well, it's the side OA prime. OA prime. This is our trusty setup that always seems to work. So here we cross multiply this ratio and we obtain that the product of the distances from the center of inversion to the pre-image point A and from the center of inversion to the image point A is equal to precisely OB squared, which in our case is precisely the square of the radius of inversion R. The points O, A, the pre-image, and A prime, the image, are collinear. They all sit on one and the same straight line L by construction. They're all coplanar, so condition 1 of definition 1 is honored. The condition 3 of definition 1 is honored. This is our, remember, this is our workhorse relationship that will work for us many times. That is honored. And what is the last piece? Well, the definition 2 of the negative power of inversion. The center of inversion is located in between the pre-image and the image points as per the axioms of geometry due to the German mathematician David Hilbert. Game over, problem solved, a proof is constructed. But now we will mark this problem with the completion sign, the empty square. But now if we carefully go back to the solution of the problem number 2, we will discover that our steps that locate the image of the given point under the inversion of the plane with respect to a circle with negative power are actually symmetrical or one and the same, regardless of where the point A, the pre-image point, is located with respect to the circle of inversion. Whether that pre-image point is located strictly inside of the circle of inversion or strictly outside of the circle of inversion, the same 4 steps taken in that order work. They produce the image of the given pre-image point correctly both times. But if we go back to the solution of the problem number 1 and the problem number 3 and juxtapose the two, we will see that that is not the case. When the power of inversion is positive, the order in which we take our constructive steps in order to locate the image of the given point does vary and does change with respect to location of the pre-image point in reference to the circle of inversion. When the pre-image point is located strictly inside the circle of inversion, we construct the tangent to that circle. Last, but when the pre-image point is located strictly outside of the circle of inversion, then we construct the tangent to that circle first. So the objective of the next problem, problem 5, will be to invent or discover, pick your favorite verb, a constructive algorithm that uses nothing but the Euclidean tools alone for the recovery of the image of the given point when the power of inversion is positive, that is symmetrical and works the same way whether the pre-image point is located outside of the circle of inversion or it is located inside the circle of inversion. And at the beginning of next problem, I will highlight, bring it front and center, the problem with the construction of the inverse image of the given point when the power of inversion is positive. That is, in the problem number 5 of our course, we're asked to go to the solutions of the problem 1 and problem 3 and realize that when the power of inversion is positive, see with the plus sign, then the order in which we carry out the constructive steps in order to locate the image of the given pre-image point under positive power are different. That is, when the pre-image point is located strictly inside of the circle of inversion, then let's say we draw the line L, as we refer to it, all the same first here, and then this is where the deviation from the construction of the image when the given point, pre-image point, is located outside of the circle of inversion begins. Because now, after the straight line L is constructed, see, we do it first both times. Then first we construct the perpendicular P. I marked it here with the step number 2. P is constructed as number 2. And then, after that perpendicular to L is constructed, we construct the tangent. This is the step number 3, the tangent tau. But if the pre-image point is located strictly outside of the circle of inversion, then under positive power inversion, let's say we still draw the same straight line L, but now we do not construct a perpendicular to L. We have nothing to construct it meaningfully through. We first construct the tangent tau, so that will be the step number 2 in this case, and only then we construct the perpendicular. So now I just want to make sure that all of our viewers are on the same page and all of our viewers understand what is the problem, what is this with this construction. Technically, there is no problem. This construction works either way. It is technically correct, but it lacks symmetry. So here, when we compare this solution of the problem 1 and 3 to our solution of the problem 2 and 4, we see that regardless of where the pre-image point is located in reference to the circle of inversion, the same steps work, unlike the case when the power of inversion is positive. Make sure that you understand, you grasp this idea well. Whether the pre-image point is located strictly inside or outside, the steps are the same. Straight line, perpendicular to that line through the center of inversion, intersection point, straight line through the pre-image point, either here or here, through the point B, works either way. And then what? A straight line that is perpendicular to that straight line, either that way, here, or that way, here, locates the sought after image. So that construction, when the power of inversion is negative, is symmetric. But when the power of inversion is positive, our first take is technically correct, yes, but it is not symmetrical. So the idea is to put your thinking hat on. As you will see right now, there is no symbolic manipulation. You will be doing mathematics, you will be shuffling ideas, you will be failing. You will be trying again, failing again, trying again. Maybe some people will give up, some people will not give up, but the idea is here, give it an honest attempt, give it an honest go, and try to come up with a construction of the image of the given point under the inversion of the plane with respect to a circle when the power of inversion is positive, that is symmetric and works both ways, similar to how our constructive steps for the recovery of the image of the given point under the inversion of the plane with respect to a circle when the power of inversion is negative works both ways or is symmetrical. And in a sense, this is what mathematicians do all day long. Of course, they do not manipulate the elementary material as we're doing here, but in its essence and in its spirit, we have a problem that is open-ended. There is no plug and chug situation which can help us. There is no algorithmic guidance of any kind. We're just asked to invent an algorithm that will do the right thing symmetrically. How do we attack this problem? Well, precisely this is the essence of what mathematics is: solving open-ended problems, exercising your technical wits, using your powers of improvisation and technical ingenuity, and figuring out how to solve the problem. So here is one way to solve this problem and how to come up with an algorithm that is symmetric. So we have a point A that is either distinct from the point of infinity, or the point A, the pre-image point, that is distinct from the center of inversion, because then we have something interesting and meaningful going on where we can exercise our wits. So let's say this point first is located strictly inside the circle of inversion. When the point is located strictly on the circle of inversion, we already know what's going on with the power of inversion. That is, let me write it down here just to make sure the power of inversion is positive. That point remains what? Fixed, and the whole shape is called invariant. So first thing that we do, let's do this together. First thing that we do is, just like in the previous steps, we draw a straight line through the center of inversion and through the given point. We will call this straight line L again. We will call this straight line L. Let us record this step carefully. Step number 1, the straight line L, that is by definition a straight line that passes through the center of inversion and the given pre-image point, regardless of where that point is located. That point could be located inside or outside. That step is one and the same. So far, so good. That step is symmetrical. Straight line L. We will refer to it as the step number 1. Next, here is the cleverness of this idea. Next, what we do seems a little arbitrary, if not to say frivolous, but amazingly enough, it works. What we do is we construct, well, depending on how you want to verb it, a chord or a second of the given circle of inversion through the given point. We listen carefully. So if the point is located inside, that's a chord, but if the point is located outside, what will it be? It will be a second. Thus, we throw out this idea with the chord, we polish it with the terminology which is more correct. We construct a second of a given circle of inversion through the given point. In this case, the point is located inside of the circle of inversion. That's fine. So we go like this. For example, we construct a second. We will refer this to this straight line precisely as S. For second, lowercase s, through the point of through the pre-image point that is given. So the second step will be a second that is given through the point A such that this second intersects the circle of inversion at 2 points. We have A taken, let's call them B and C, it doesn't matter, B and C, 2 points. So here we have it, the point, 1 point and another point. Again, our terminology is that it's a second. The straight line is a second. So we will mark it carefully with number 2 here. And let's say this is our point B. This is our point C. Next, we take the point that lies over here. And again, we'll have to play with the terminology once we settle it in. Let's say we pick this point, and through that point B, we draw now what? This will be our step number 3. This will be our step number 3. We draw a straight line that is perpendicular. We will call that straight line P. It will be perpendicular. P is perpendicular to our straight line L, perpendicular to L through the point B. And again, you see, we'll have to, once we present the polished solution, we'll have to find the right words to say what this point is. Through the point B, this angle is right. There will be some point over here, and there will be another point over here. Let's say P will intersect the circle of inversion evidently at the point B again, and at the point D we have another point. We generated another point, D. This is our point D, and this was 1, this is 2. We carefully record this as a straight line 3, and that's it. We're home free. We have a straight line right now. We have 2 distinct points, C and D. And the straight line through these points will intersect. The straight line through these points will intersect the straight line L precisely at the point sought after. Of course, with my drawings that are done by eye, this is not very precise. These points should be somewhat close, but here I will not mark the points as A prime or A. I will just designate them like so. And the claim here is that this point here is the inverse image of this point, and conversely, this point is the inverse image of this point with respect to the given circle when the power is positive. So the step number 4 will be to draw the straight line DC, which will intersect the point L precisely at the image point. Image point sought after. Boom, problem solved in 4 steps. Now we need what? We need a proof that this is really so. Well, we'll knock out the first things first. The points O, the center of inversion, and the 2 points that we obtained over here are collinear. Game over. Now, these 2 points are also located on the same side of the center of inversion, O. That game is over. So we have 2 conditions already knocked out, honored. So now we need to prove that these distances, the products of these distances, are indeed the square of the radius of inversion. Well, let's say we give these points some names, because then otherwise it will be difficult to work with. A, let's say this point is A and that point is A prime. We will rename these points later on. So what is important to realize over here? Well, first thing, for a proof, how do we prove that? What do we need to prove? We need to prove that the distance from O to R to the pre-image point times the distance from the center of inversion to the image point is precisely R square because all the other components of the image we already took care of. That's the last thing that we need to do. Well, the proof here is actually quite elegant. Let's carry this out. Let's talk about this proof. Let's connect the point D with the point O. Let's like this and like so. You see? So what does it tell us? Because the straight line P is perpendicular to the straight line L that contains the center of inversion. That means that the distances from this point to the point D, this distance right here, is the same as the distance from this point to the point B, to this distance right here. If you want to give this point a name, be my guest, A, B, C, D. This point here, another point will be E. We may or may not need it, and this point will be F again. We may or may not need it, but if you want to write it down more formally for a polished presentation, definitely you can do that. Now, let me move this point out of the way. We all understand that this point is O because we will need it right now. Let us see what is going on here. First of all, we already know that we need, in order to construct this relation that honors the condition 3 of definition 1. Previously, we shuffled the advantageously positioned right triangles. Here, we do not really have right triangles. Here we have this distance right here from the center O to this guy. And then we have this distance. So this is kind of seems to be awkward, but not really. Look at this. Because the distances from the point D to the point O and from the point B to the point O are the same. This is R and R. The triangle DOB is what? Isosceles. Wonderful. So now we reason which way? The central angle DOB, the central angle, is by the corresponding theorem from the theory of circles developed by Euclid is what? Is twice the corresponding angle in the circumference. Thus, if our straight line OF or OE, you see our points came in handy, is the bisector of the interior angle, because this angle is right, isosceles triangle, these sides are of equal length. Let's mark them so. This is equal to this, just to be sure. What is 1/2 of this angle? What is 1/2 of the angle DOB? Well, it's this angle right here. You see this guy. And which angle in the circumference subtends the same circular arc, CEB? You see the point E came in handy again. Well, it's the angle that has vertex at the point C. That means that the magnitude of the angle EOB or FOB, if you will, is equal precisely to that angle right here. See? Let's start giving these guys names. This is alpha, and then this is angle alpha. Why is that? Well, twice the magnitude of alpha is the central angle. 1/2 of it, alpha, is the angle in the circumference that subtends the same arc. Game over. Very nice. Next, the angles at the vertex A formed by the straight line S and L are what? Are vertical. So this angle, what's the beta, and this angle beta are the same. Wonderful. Now let's take red chalk. The straight line DCA here forms what in terms of angles? It's the angle that is pi in magnitude. So that means that this angle right here, let me make it wavy like this, alpha, beta, gamma, is equal to which angle? This angle right here, right? Would you agree? Angle gamma. Now we have which triangles? Let's concentrate on the triangle BOA and CAA prime. Vertical angles, same angles. It means that these angles here, theta, must be the same. Would you agree? I hope I have enough decorations here to make these angles distinct. But the same thing can be said about the angles in this triangle. Here, this guy is alpha. And then consequently, this angle is also gamma. But now in the smaller triangles CAA prime and DOA prime, what angle is shared? The angle at the vertex A prime. Beautiful, isn't it? Here. That means that the remaining angle in this triangle ODA prime must be what? Look at this. Let's compare it carefully. Theta, theta, gamma, gamma. So what angle is missing over here? Theta, theta, gamma, gamma. It must be beta. That's right. So that angle must be beta over here. I use 2 beta. Game over. With us proved just now by straightforward manipulation, or the so-called angle chasing, as they say in Olympic mathematics, we proved that the triangle, which one? BOA, is similar, whatever the symbol is, similar to the triangle DOA prime. Triangle DOA prime. And the angles in these triangles run as follows. Theta in the smaller triangle here is theta here in the bigger triangle. Gamma and gamma, they're equal due to isosceles triangle and central angle twice the angle in the circumference. And the beta here and beta over here. That's it. Game over. Now we bring in our favorite Euclid's Elements, Book 6, Proposition 4, if I'm not mistaken. This is the theorem that says that in similar triangles, or as Euclid refers to them, equiangular triangles, the lengths of the sides about equal angles are in the same proportion, where the corresponding sides lie opposite equal angles. So let's splice our material that we need. We need these guys. So in the triangle BOA, what do we need? We need the distance OA. OA, exactly. In the triangle BOA, the side OA lies opposite the angle theta, you see. Which side in the bigger triangle DOA prime lies against the angle theta? Well, it's OD. OD. Wonderful. Now we relate the side OA to the side OB. OB, which lies in this triangle against the angle beta. In the larger triangle against the angle beta, which side lies? The side OA prime, exactly what we need. OA prime. Look at how beautiful these things come out. Cross multiply. From here it follows that the distance from the point O, from the center of inversion to the pre-image point, it times the distance from the point O to its image is precisely what? OB times OD. OB is equal to OD is equal to R squared. Game over. Isn't that beautiful? It's absolutely beautiful. All we had to do is exhibit some play of thought, and this is what mathematics is. It's a play of thought. A thought is the first-class citizen in mathematics, not the symbolic shuffling. We can rigorize and formalize all these 7 ways to Sunday. Nobody cares about this, and this rigorization will be all but unreadable. But the playful, the joyful, the pleasure of doing mathematics is precisely in this, figuring out how these ideas come together. Now, why do we claim that our solution is the right one? It's symmetrical. Why do we put the square here and say, okay, game over, problem solved, proof is correct and complete? Why is that? Well, let's play this movie, so to speak, in reverse order. Let us say that the point A is now our pre-image. We will remove the prime qualifier from this letter. Now this is our pre-image, and now this wants to be, now this imposter over here wants to gain the membership in the exclusive club of inverse images. Is he an imposter or he is a real deal? Well, let's think about it. When the point A is located outside of the circle of inversion on the positive power of inversion, the first step was to construct the straight line L through the center of inversion in the pre-image. Boom. Done. What's the second step? Come up with a second through the pre-image point in such a way that this second intersects the circle of inversion at two distinct points, which we call B and C. Well, where is that second on this drawing? Here it is. This is the second. This is our straight line. It's the same straight line that we had in the previous step, but it follows exactly the same scenario. Yes, we will see that the points D and B trade places in our algorithm, but essentially our algorithm still works the same way. What is the third step? Construct a straight line P perpendicular to L through the point B. Well, in reverse order, the point D became B, and the point B became D. But this is just cosmetic renaming. It does not change the technical spirit, the technical essence of our constructive algorithm. The perpendicular P to the straight line L, perpendicular P to the straight line L, exactly the same way. Boom. And what is the fourth step in this construction? The straight line DC intersects the straight line L at the image point. What is the straight line? Now remember, DC is this guy. Once this straight line intersects the straight line L, boom, it will mark the spot. And indeed, the green point A prime is not an imposter. It's a real deal. It's a genuine image. Our algorithm is symmetrical with respect to the location of the pre-image point in reference to the circle of inversion C. It works regardless. So in this respect, following these steps in this order, 1, 2, 3, 4, we recover the image of the given point under the inversion of the plane with respect to a circle when the power is positive. This is a beautiful problem, and it has a converse, depending on how you want to name it. It's perfectly fine to name it a theorem. And this converse theorem you should think about on your own, try to prove it on your own. And the statement of this theorem goes as follows. If the points A and A prime, which can be swapped any which way legally, are the inverse images of each other with respect to a circle of inversion C that has the center of at the point O and the radius R, then under the construction that follows over here, the points B and D will be the images of each other with respect to the straight line L. Remember, so this, for the converse, the burden of proof is that the distance FD, the distance, let me write it down, where over here, the distance FD is equal to the distance FB. That's the burden of proof on the converse theorem, because remember, in our step number 3, we demanded that we construct this perpendicular. That was our will. We did it so, and by that virtue, this relationship is correct. But then from this assumption, or our will, if you will, from our forceful, let's say, decision, we prove that these points are the inverse images of each other. With the converse statement, we take it that these 2 points are the inverse images of each other, and we unwind it back into the fact that it must be the case that the distance from the point F to the point D and from the point F to the point B must be one and the same. Try to prove this theorem on your own. Think about it. Meanwhile, we're almost done with this episode 3, lecture 3. Before we call it a day with this episode, I would like to show you guys how we can construct all these perpendiculars, because we constructed so many perpendiculars through a point, to a straight line through a point, that I want to make sure that you do not think that Roman is lying to you, but it is entirely possible to do that, to carry out that task with Euclidean tools alone in precisely 3 steps. The final segment of this episode is optional. It is for curious travelers only, and for those people who want to know for sure that Roman is not trying to pull a fast one over here with all his empty and nebulous promises that, oh yeah, it is always possible to construct a straight line that is perpendicular to a given straight line, lambda, through a point P on it, with Euclidean tools alone, a straight edge and a compass in precisely 3 steps, because most, again, if not all, students are pretty either familiar or can generate a quote-unquote standard 4-step algorithm by starting with the circle that is centered at the point P, obtain 2 points that are equally distant from the point P, and then construct 2, 3, and 4 as the straight line. But remember that on this channel, this is who we are and what we do. The pressure to be creative and inventive is relentless, always nonstop. Be creative, be inventive, accomplish this task in 3 steps. Think on your own, put this video on pause, go away, give it a thought, come back and compare your idea to ours. So here is the 3-step solution for constructing a straight line that is perpendicular to a given straight line, lambda, and passes through a point P on that straight line. Step number 1. It is a little bit slippery, but the idea here is the following. Open up the compass, Euclidean compass, to the distance that is guaranteed to be larger than the distance from the center of that helper auxiliary circle number 1, then the distance, then its radius. In other words, we want to make sure that we construct a circle shown over here in such a way that its radius is larger than the distance from that center of the circle to that straight line lambda. So here, this step is somewhat slippery. How do we know? Well, this is the idea. That circle, which will be, we will mark it as step number 1. This is step number 1. At the center over here, let's say all the auxiliary objects we will mark with the orange. This is the center. The circle will intersect our straight line lambda at 2 distinct points. The point P, by design, this is what is given to us. And the second point over here, let's say call it Q, that will be distinct from P. And the game is over. What do we do now? Well, we unleash the Thales' theorem onto this mess. So we construct a straight line through the point O, the center of our auxiliary circle, and the second point of intersection of that circle with the straight line lambda, Q, in such a way that that straight line will intersect the constructed circle at two distinct points. One such point will be Q, shown over here. This is the point Q. And the other point, we'll call it S, such that what? The distance SQ will be a diameter of our helper circle number 1. This line, the line shown in orange, will be line number 2. But the game is over, because now we see that the straight line through the points S and P, is precisely the straight line through the points S and P is precisely the perpendicular, let's call it P, thought after, forms the right angle with the given straight line lambda, and that straight line is the step number 3 by the rules of straight edge and compass construction. This is precisely a 3-step construction, because naming points in this game of constructing things does not account for a step. A step, or something that carries the cost of 1, is the act of drawing or constructing a curve, or a line, if you will, that was not present in the construction prior to this step. And so here are the steps. Pick a point O that has the distance to the point P that is greater than the distance from that point to the straight line lambda, because we want, why? Because we want a genuine intersection at two distinct points. No intersection or tangency is not going to work. We need precisely 2 points, and here perhaps some of the more pedantic viewers will say, hey, how do we know that this is the case? Well, perhaps this is a slippery part, but practically it is always possible. So pick a point that is distance from the straight line lambda further away than it is from the distance from the point O to the point P is larger than the distance from the point O to the straight line lambda. First, construct a circle through the point P centered at the point O. Obtain the second point of intersection of that circle with the straight line lambda. Construct a straight line through the second point of intersection and the center O. Obtain the second point of intersection of that straight line with the circle, and through that point draw a straight line that connects the given point P. Voila, by Thales' theorem, we have the angle in the circumference that subtends a diameter of the circle, and that angle must be right. Problem solved in 3 steps. This is it for episode 3, lecture 3. Thank you very much for your time. Thank you for watching. I will see you in the next video, which will be episode 4, lecture 4, in which we will continue the study of how the inversion of the real plane with respect to a circle acts on points.